Let's start first some points from kinematics. So when we have to find the distance covered, like we have to write the equation of the elemental distance dr in this form. If it is 2D motion, then we have this form. If it is 3D motion, then we have dx square plus dy square plus dz square form, and we can convert it into such type of form by taking out one of these dx, dy, or dz outside, and we get the slopes along, or slopes like dy by dx or dz by dx when we take out the dx, and then we can integrate in terms of dx this whole equation, and the integration would give the total distance covered. And now rotation of a vector, when there is a unit vector, any vector given that is rotating in the space, it is not necessary that it is fixed at one point and rotating. It is possible that it is also changing position but also rotating. So the rate at which the theta, this orientation, is changing, let's say this is rotating with some omega about its frame at any point, then it is, if it is rotating with some omega angular velocity, then the dA by dt value, means time differentiation of this unit vector, of this vector, that would be equal to omega vector cross a cape, because this is a unit vector, we will take a cape. And if we have to take the differentiation of the complete vector, that is magnitude and unit vector, then we have to differentiate magnitude separately, and then the differentiation of unit vector would give this equation, and the time differentiation of a rotating vector would give a value, would give a vector in perpendicular direction to both omega and a. Now average value is given by the final minus initial divided by the time, and here we have to note that the acceleration is equal to this vx dv by dx. If we take dx here, then this value would be vx, and if we take y dy, then it would be vy. It would not be completely v vector, but only vy with positive and negative sign accordingly. And now we have the total acceleration equation. Total acceleration is given by a acceleration is equal to a perpendicular plus a parallel. So we have total acceleration a net is equal to a perpendicular plus a tangential. This can be called a normal or a radial, like a radial or a normal. And this is a tangential. This a tangential is along the path of the body, along the tangent of the path, and this component is perpendicular to the path, and the direction of this vector would be taken toward the center of the curve. So any curve would be treated as a part of a circle, and the radius of that circle is of the path is called the radius of curvature, RC. And the formula for RC is for a 2D motion. In case of 2D motion, we have the formula for radius of curvature, which is equal to 1 plus differentiation of y squared bracket whole raised to the power 3 by 2 divided by double differentiation of y. This differentiation is with respect to y dash is equal to dy by dx. So this gives the radius of curvature. It can have some positive value or negative value. So accordingly, we get the curve either outward or inward, means upward or downward curve. So this type of curve will have, let's say, one sign, and this type of curve will have other sign, means because it is curving downward. And the tangential component changes the magnitude of speed, not the direction, and the perpendicular component changes the direction and not the speed. So these two have different functions, and this a perpendicular is equal to net velocity square divided by the radius of curvature, and the direction is toward the center. So let's say the RC vector is drawn from the center towards this point where particle is. So let's say this is the center, then we have to draw the RC vector in this direction, then the minus of this RC vector will be the direction of this a perpendicular. And then we have the concept of average. Just if we have to take average with any quantity, let's say we have to take average with time, then in that case we just take the function and differentiate with ft in a time interval. Average value is always calculated for an interval, and we have to integrate this and divide by the interval of that value. If it is time, then we have to divide by the interval of time. If it is taken average with respect to the position, that is x, let's say x coordinate, then in that case we integrate with dx from in any interval, and then we take the change of x in that interval. So this gives the average value. We can take average for any vector or any scalar quantity also. The next thing is angular velocity, finding the angular velocity of any line, So because lines make angle, so we can define the rate of change of the orientation of the line, means the rate at which the line is changing its angle from the initial. Let's say the line was initially at this state, then it moved here, so the angle changed by this line, that d theta by dt, that is the omega, and that is given by simply take any 2 points on this line. And if we know any 2 points on this line and we know the velocity of those 2 points, we have to take the velocity perpendicular to this line joining these 2 points, and consider one of the directions perpendicular to this line as positive, then either both would be positive or one would be positive and other would be negative, and take the difference of both speeds and divide by the length between them. So let's say if there is a line like this, I take 2 points on this line A and B, and let's say this is moving with v velocity in this direction and va velocity, this is moving with va velocity in this direction. So I have to first take the vb component perpendicular to this line of length L, and similarly component of va perpendicular to this length, that is va perpendicular. Now let's say I take this direction as positive, then this, if it is positive, I will take this as positive and this is negative value. This was the magnitude and I took a negative sign with it. Now I have to take vb perpendicular minus of minus va perpendicular, means difference of both velocities, and we will take the magnitude divided by the L. So that becomes vb perpendicular plus va perpendicular divided by L. That is the magnitude of omega of this line. That is the rate at which this line is rotating. And to tell the sense in which this body is rotating, we can simply see that this point is moving in this direction and this point in this left direction. So if we try to rotate the line in this sense, the thumb will point inward the page. So omega is inward page because this line is rotating in this sense. Now this is omega. Now we have graph of ax where this relation can be used, that a into dx integration gives vx dv integration, that is delta v square by 2 is equal to the integration of ax, that is the area of the graph. And then in this vx v square x graph, we can have this 2a as the slope, and we can derive it from this equation. Where is that equation? V square minus e square is equal to 2as. So if we take u square as constant, then we get differentiation of v square, which is equal to differentiation of 2as with respect to this s, then we will get 2a, that is the slope. And that's it. So we can use Snell's law for some kind of calculation for when we have any two mediums with different velocities of body and we have to find the fastest path. Then in that case we can use the Snell's law, because light also follows the fastest path, but the only difference is that light travels at some high speed while the objects we are given may move at very small speed, but still for the fastest path the path remains same, velocities may be different, and we have to make sure that the case is similar to the case of light. So let's say if it is moving at a larger angle at this side and smaller at this side from this normal line, let's say, means the normal should be drawn perpendicular to the interface again here, and let's say it is moving this medium with v2 speed and v1 speed in this medium, then so let's say this was the surface and this was v2 and v1 speed of them, and this was normal. So if the speed in this medium is larger, then this theta1 should be larger than theta2. So the larger medium should also have larger angle. That is the condition. That is the condition to apply this Snell's law. And we can apply for critical angle also. Now for problems like a solid body and on which the body means a body is moving on its surface, not in its 3D medium but only on its surface, means on its surface it can move but it cannot take any diagonal path or any other path inside space. Then in such cases we have to try to open this whole 3D surface in all possible ways and try to find which is the shortest path. For example, this is a cuboid shape and a person has to crawl from this A point to the B point. Then to find the shortest path we have to just travel along the surfaces. So we will open this box and see which path is the shortest. We will try to open it in many ways, like let's say if we have to open this, how will we open it? This is a cuboid, so let's say this is point A and this is point B. So when we open it, let's say this was the base with this point B, and if I open it in this way, this goes in this way on this, and this will open in this manner, and again this whole top can be opened like this. Now this A point was in contact with this point, let's call it A star, or let's just call it A, and then this point was also in contact with this point, so let's also call this point A. So these 2 points were in contact with this A and this point was here at this point. So we just have to find which is the shortest path, one of these and one of these, and that's it. And if we were opening this in this manner, let's say in this manner, then this point would be again A, and we can calculate this AB length again. So we will get these 3 possibilities and these 2 lengths are equal. Okay, so that's it. Just calculate the lengths and compare which is shortest. Now for writing any vector in terms of other vector, let's say 1 with respect to 2, we can introduce many other vectors between this 1 and 2, like 1 3 3 4 4 5 5 6, and then 6 2. Means it will start with 1 and then end with 2, and all will be added and can be used for any vector, can be position, velocity, and velocity, anything. And then this for drift problem, when the velocity of boat in still river is greater than the speed of river, then we can completely cancel out this. We can completely we can project the body at, let's say the river is moving with some VR speed in this direction, then we can launch this boat at some angle so that its one component cancels the speed of river and it moves in straight path. Then in that case the drift would become zero. But if the speed of this boat in still river is not greater than this or maybe equal to this, then in that case, first of all, when it is smaller than that, then in that case we cannot cancel out this its component would always be smaller than its magnitude, and that would always be smaller than the speed of river. So the boat will always be drifting in sideways if it is trying to move in this direction. If the boat is drafting in this direction, and the boat would slide in this manner, but also, okay, so the boat will move in this manner but point in this direction. And for such case there would be some drift, and that the angle at which this boat is drifting from the vertical line, that is vertical line is means this is the river flowing in this manner, then this is the vertical line joining the two sides, and this theta angle is given by this, means sorry, this projection angle should be this way. So the angle at which this boat is projected, that angle is theta. So that is the angle of projection of boat with this vertical line, that is theta. So if I project it at this angle, there would be minimum drift. So this is the case, and remember that sin theta is smaller than equal to 1. Now for chasing problems, we have to write one equation of the separation equation, velocity of separation, that is the rate at which the length between the two points is decreasing. We have to write that equation, and we know that to catch the person, the distance would reduce to 0. So we know the initial distance between them and the final distance between them. That would give us one equation, and another equation would be depending on, for example, in this case there are two persons and they both are chasing each other. So the distance traveled by this person along this path up to this, and this person will travel path up to this, and they both will travel in the same time. So they have a restriction or a constant of time that they must meet each other at the same time. So the distance this travels and this travels, we can add this component, this horizontal component of this line, and these two lengths when added give the length traveled by this point. So we get one more equation. So in this way we can form one, two, or generally two equations, and we can solve for the time of catching. Now we have said projectile motion under gravity when there is a horizontal, sorry, it is not necessary that we have a horizontal surface. We can have any surface. Let's say this point is origin, taken as origin, and this body is released with the v velocity at some theta angle with the horizontal. Then all the position in the spaces that it may occupy, that is given by this equation, and it can be converted into this form: tan theta x bracket 1 minus r upon x upon r, where r is the range along the horizontal path. Means let's say I draw a horizontal path from passing through this 0 0, then the point at which this intersects with this horizontal line, the distance up to that point will be range of this. And there is one more concept, that is safety parabola. So safety parabola concept is that when we have a body, let's say this is origin, and we have a body that is free to be launched in any direction, then in that case the let's say we have a fixed speed value, then if I release it at some angle, it will fall like this. If I increase, it will become like this, and at 45-degree angle the range would become maximum at 45 degree, and then it will start decreasing again. And if I touch the extreme points of these all trajectories that are outward, means the most exterior points of these parabolas, if I join them, they will form a shape like parabola. And similarly we can do this in this direction. And so the maximum point they can reach, the farthest point this body can reach with this v speed, is this safety parabola. This means it can only touch this point, it cannot go outside this safety parabola. And because we know that the range, now first point is that this shape is parabola and the body cannot go out of this, that is the maximum point it can reach. And the maximum height is v square by 2g, and the maximum distance is v square by g, that is v square by g sine 2 theta, that is the maximum range. Now to write the equation of safety parabola, we can use, we know that these two are the roads. This is minus v square by c, and this is vertex, that is 0 comma v square by 2g. And we can solve this and get the equation of y and x, and the equation would be this: y is equal to minus x square g by 2v square plus v square by 2g. And the property of safety parabola is that because this is the extreme point at any speed. So if I am given any x position and I am asked what is the maximum height I can reach at this speed, so I will say that to find this maximum height I will use this equation. I will put the value of v and x, and maximum height would be the height point on the safety parabola. And if I am given any point here in the space, let's say xy, and I'm asked what is the minimum speed, so that if I launch it from this point I can reach this coordinate. So again, for minimum speed to cross any point, that's xy, we can use this equation again. Means this point, if it would be lying on a safety parabola, then the speed would be minimum for it. So I have to just put the point on the safety parabola to get the condition of minimum speed. And so these are some equations. We have, first of all, speed. To find the speed, so we can use this relation for speed from the y and x coordinates, and tan theta naught means if there is any point on the safety parabola at some x naught coordinate, that is any this point, and if I want to hit that point, then at which angle I should release the body, then that would be theta naught, and that is given by only v square and gx. Means we need only two values, speed and the x coordinate, because y is already defined if we define these two values. And we have in projectile motion the horizontal component of the velocity is always constant, so v naught cos theta at a starting point would be equal to, let's say v is the speed at any point and that max and alpha angle at any instant, then v cos alpha would be equal to v cos theta. And this is the equation of motion under constant acceleration. So now we have equation on a slope, which I am not telling. You can see this is a radius of curvature equation. In case of when the equation of parabola is this, y is equal to ax square, we have the radius of curvature at this point. This point is curved, and the radius of curvature at this point would be the coefficient of x square, reciprocal of it, and twice of the reciprocal of it. Sorry, reciprocal of twice of it. So 1 upon 2a is the radius of curvature here. And in case of parabola, at this point there will be some radius of curvature, and at this point there will be some radius of curvature, and the values are, let's say this is length a and this length is b. Then in that case, for this, let's say this is a length, for this a length the radius would be given as b by a square, so b square by a. And for this b part, the radius would be given by a square by b, means swapping the values a and b. For b we get a square by b, for a we get b square by a. And you can also remember it as the, let's say this is large and this is small, then this larger part should have a smaller curve. So smaller curve means smaller length should be above and larger should be below. So that's why this curvature is b square by a. And equation of motion under uniform acceleration, we have this equation, this. And now if a body covers equal distances, we have this formula, but we can derive it, not need to remember. And graphs like position can start from any point, and displacement always starts from 0. Distance also starts from 0, but it is always increasing, and displacement can be decreasing, but the point at which this starts decreasing, this displacement starts decreasing, we just have to flip this upward to get this distance graph. We can predict the distance graph from the displacement graph, but to predict the displacement graph from the distance, it is not possible. Now one more important formula we have for ease in solving questions. We have t is equal to root th by g, means when a body is dropped from some h height, then the velocity it would have just before falling, that would be v square, v is equal to root of 2gh, that is the height. And dropped means it is dropped, it started with 0 velocity, then the final velocity will be is equal to root 2gh, and that also is the velocity at which you have to throw, so that it stops at h height. And then the time it takes to drop, or if you throw it with that v speed, if you want to make it reach at that height h, or to drop from the height h, then in that case you have the time of the journey is equal to root of 2h by g. And this process is under constant acceleration, and this is for pulley. So there are two constants, that in a rigid body the distance between 2 points cannot change, so the velocity of a along the line, well, relative velocity of these two along the line should be 0, means the dl by dt between AB should not change. That is used to solve constant problems. Now going to NLM. So we have, I think, just a force equation of external, because in the net force on a body, on a system, internal forces cancel out, we get only external force left. And if there are 2 points very close, then the work done by these action reaction forces will also be 0, because these 2 points have same displacement, and the torque on these two bodies when added, that would also be 0 due to this internal force. And so the average force is given by the total impulse divided by the total time, that is impulse is total change in momentum divided by the total time, that is delta p by delta t, that is the average value. And dm is in this equation mdv by dt plus dmv by dt. The velocity is the speed of the center of mass, velocity is the speed of center of mass of the system, mass m is the mass of the system, dm by dt is the rate of change of mass of system. It is positive if it is increasing, negative if decreasing, and dv by dt is the rate of change of the center of mass of the system, velocity of the center of mass of the system. So this can be written as macm. If mass is constant, then we get this equation f external is equal to macm, which can also be written in this form. And if I integrate this f dot dx, then I get the equation of mv square by 2 mvx, sorry, if we have f, okay, sorry, okay, one more thing, when we have to find out the force applied by any colliding mass or any living mass on a body. Let's say there is a rocket here, and this rocket is leaving some mass with some velocity v. Let's say this is moving with the velocity v1, and this is leaving some mass with the velocity v2 in this direction, opposite direction. Then to find out the force applied by this leaving mass on this rest mass of the body, that would be equal to the rate of the change of mass, that is dm by dt, into the v relative vector, where v relative is given by the velocity of this minus velocity of this, that is v2 vector minus v1 vector multiplied by dm by dt, that is equal to f vector applied by this mass on this rocket, this removing mass on this body. And this v2 velocity is the velocity of this body after this gets released, means initially they were moving with the same speed, now they are moving with, they are separated, means before they were attached and now they are separating. This was this case v2 minus v1 vector. Now if we have any other body, let's say a rocket, and we are hitting some dm by dt mass on this body with some v2 velocity, and this is moving some v1 velocity, then the force applied by this dm by dt mass hitting this body and getting attached to it. So initially it was moving with v2 velocity, and now it is getting attached to it to move with the same velocity v1. And then we have to take f is equal to dm by dt again, but now here in this case we have to take v2 minus v1 of this initial velocity v2 minus v1 vector. In this case this was the final velocity v2 then minus v1 vector, and the dm by dt would be taken negative if it is removed, and it would be taken positive if it is added. So that's it. Now for finding the normal forces, the normal force always acts perpendicular to the normal to the mutual perpendicular of the surface. So if any surface is like this and another is this, then we have to take the, let's say this is the contact point, then the normal at this point will be the direction of the normal force. And if I take this point as pointed one, then I don't know the surface direction of normal of this surface, but I know the normal of this surface at this point. So again this would be the normal. But now if I take the point in this manner, both don't have any normal defined, then in that case we have to take some any random direction of normal with some theta variable, let's say n in this direction at some angle theta, or we can take it like ny and nx, means we have to take two variables in case of 2D plane. And now the string and spring case. So let's say we have a string that is inextensible and massless. So both massless spring and massless string, when we compare them, we have, let's say, a spring here of mass m, and mass m is also connected here, and a mass m1 m2 m3 this way, and there is a string here connected to this m1 m2 and then this m3 with a pulley here. Now this system is, let's say, at equilibrium. Now if I cut this, then the force between them would remain same, but if I cut this, the force between them will change, means the force can change instantly in a spring, but in a spring the force may not change instantly because there is some significant expansion x in this spring, while this spring is inextensible with almost zero extension, we can assume. So this extension can change, this almost zero extension can change in a very instantly it can change. So that's why when we cut it, the tension changes instantly, but in this case this cannot change instantly. But now if I remove this m2 mass and join this mass directly with this m3 mass, and if I cut it now, since one end of this spring has mass but other has no mass, then this spring is, because it is massless, it can have infinite acceleration, and the tension in the spring would instantly change. So now in this case it will instantly change because there is no mass on both sides, only one side there is mass. Okay, so one property of, so this is the spring force, but one property of a spring force is that delta f, that is a change in force applied by the spring. Change in the force applied by the spring is equal to the minus k delta x, that is equal to the change in the extension of the spring, and this would be valid as long as the string does not slack. Spring does not slack. No, string doesn't slack, so we don't have to worry about this. So this is the valid form, that a change in, that is change in this, what we say, force of the spring is equal to this minus k delta x. The more is the change in extension, the more is the change in force. So we don't know, even if we don't know the absolute value of force, we can deal with the changes in the force. Now the static or kinetic friction. In static or kinetic friction, the way of solving this is, let's say there are two bodies and one is moving with some v1 speed and another is moving with some v2 speed, and let's say a1 and a2 star are some star acceleration. Star acceleration here means that if we remove this friction between them, means if the friction was absent, then would the bodies have, these bodies would have a1 acceleration, a1 star acceleration and a2 star acceleration. These are the acceleration if the friction between them was absent. We are just imagining a case. Now if the velocities of them are unequal, then that is sure that there will be a kinetic friction, and that would be away from, let's say this body is moving, let's say with respect to this body is moving in this direction, then the friction force on this body would be in this direction and on this body would be in this right direction. Now for if velocities of both of them are equal, then we will make two cases, that is either a1 star or a2 star not equal, or both of them equal. If both of them are equal, means they both are moving, they both are able to move together without any need of friction force. So because they are not sliding, then there would not be any tendency, means this means they don't have any tendency to slide over each other because they are already traveling with each other. For example, if I move my hands together in this way without any friction, they are having the same velocity, same acceleration in this direction without any friction. So if I touch them together and I move it again in same manner, there would still be no friction because there is no tendency to slide over each other because of this. So there would be no friction would be zero. But if they have different acceleration, let's say this is accelerating at some acceleration and this is accelerating at some other acceleration, but they have the same speed at an instant. So if I put them together, after an instant of time they will start to slide. So because of the change in velocities due to different acceleration, so in that case friction acts, and the friction would act according to the acceleration. Let's say this has higher acceleration in this direction, so let's say this body is having this a1 star in this direction related to this body, a1 star minus a2 star, let's say this is in this direction on this body, for this body with respect to this body, then there would be friction force on this body in this backward direction and on this body in this forward direction when it is highly accelerating in this direction. Okay, so now one more thing, that let's say there is a block here, it is at rest now, and now I connect it with a string that is completely stressed, sorry, that is let's say if that is not loose, this string is completely straight, but if I try to pull it just a little bit, there would be some tension in it. So this is the condition of this setup, and there is some friction here. So now if I apply a force to pull this mass here, then first of all the friction will act, and after the friction, if this force exceeds the friction to make the object slide, then the tension will start acting. So first friction acts and then the tension acts, and if the tension is already present in this, then let's say we can have some cases like we can start pulling, instead of applying this force F, we can start pulling this string with some tension T, then the force would act in this opposite direction with F, and there would be a situation at which, let's say this is completely balanced, this is applying some F force in this direction, this is applying some T tension, T1 tension in this direction. So after we apply force here, this friction in this direction will start decreasing, and this force will try to cancel out this T1, and if it exceeds T1, then there would be some friction force acting in this direction, and if again it exceeds this F also, then means if this exceeds this T and F, T1 and F also, then there would be some tension acting in this, means some tension would start acting, means initially you were pulling it in this direction and now it is getting pulled in this direction. Okay, so and one more thing, that if two bodies start from the rest state, then the kinetic friction won't occur as long as the limiting friction is not crossed. But it is possible that I have two bodies that are sliding initially. If two bodies are sliding from the start, then it is not necessary to cross the limiting friction, because to start the motion, if we are at rest now, then if we want to start the sliding, we have to start from static then go to kinetic. But if we are already sliding, then there is already kinetic, we don't need to cross the limiting friction. And when there is an object on the surface and there is normal that is making some alpha angle with this resultant of normal and force is called contact force, that is given as this. then this alpha angle made by this contact force when there is kinetic friction, that is equal to this. And when this static friction is maximum, in that case the tan alpha is equal to mu s. That's it. And there is one more case that is when this body, when there is a block on this slope which is having, let's say, coefficient of mu s friction, static friction is on this slope, on the surface between these two bodies, then the maximum angle of value of this beta angle, maximum angle of the slope, so that the body does not slip, so that is equal to tan of alpha is equal to mu s. In that case the body will not slip, means tan beta, this tan of this angle is equal to mu s. In that case that will be the maximum angle, so that the body does not slip over this slope. And this formula is identical to this. So one more thing, when there is a pulley with some string, let's say, wrapped around it like this, if this is frictionless if this is frictionless and also massless, and let's say this rope is accelerating with some acceleration in any case and some velocity, if I apply some if there is some T1 tension here and this is frictionless and string is also massless, this rope is also massless, in that case there would be T1 tension at the other end also. But if there is some mass of this body and this is frictionless, then let's say this part of this rope, this has some mass m, then there would be some ma force consumed. Let's say this is accelerating in this direction, then there would be some ma force consumed, and the tension at this point would be T2 is equal to, if this was massless and frictionless, that was T2 is equal to T1, but now in this case it would be T1 minus ma, because some force would be used by this mass to accelerate the acceleration. That force would be equal to ma, and because each point is accelerating with some ma, with some dm into each dm element is accelerating with acceleration, so each element will take dma force. And if there is some friction and this string is massless and there is some friction here, in that case for mass, okay, so let's say if this is friction, then this friction will start reducing the value of this tension also. Then we get T2 is equal to T1 minus summation of some friction, df friction on this element from this point to this point, so there would be some reduction of T1 tension. And there is also one type of question in which a string is wrapped around a cylinder like this, and there would be another end of it that is, let's say, loose here. So in such cases what happens that you apply a T1 tension here, and due to the friction on the surface, the other end of the point has zero tension, because this is wrapped so many times, so that this friction completely cancel out this tension, and the tension at some point of this wrapping would be zero, and there is no more tension in the rope. So at one end there is zero tension, and at the other end of the rope there is T1 tension, so only this tension force acts on this body, means this is zero, so it cannot act. But if I take any other case for a body, a rope that is wrapped like this, let's say there is a nail here and I wrap a, if I take a rope string like this and I pull it, now let's say center which is fixed, now if I pull it like this with some T tension, then there would be some T tension acting here in this direction, and there would be some T2 extension. Let's say T1 tension is acting in this direction at this point, T2 tension is acting at this point. Let's say here it is T1 at this point, and there is some friction here, and at this point there is some T2 tension acting. We know that we can cut this string in many parts, and at each point there would be equal and opposite forces, and only the forces at the end would start acting. So at the end there would be this T2 force which is in this direction, and this T1 force in this direction. So in this case there would be two forces acting, T2 and T1. But if I wrap it a lot, so that the friction T2, so that the tension T2 at this end becomes zero, then only this T1 tension will start acting. So in general, when we wrap it many times, the friction at the other end becomes zero, and we get only this force. So if I take a case in which there is a ball here, and there is, let's say, at r radius a rope is wound around it, so if I pull it with some T tension, there would be only T tension which is pulling it in this direction, and the other end would have, let's say, zero tension if this has friction. And if it does not has friction, then in that case either the other end would be attached to any point, let's say with a nail it is attached at this point, then we need to know what is the position at which the other end is. If there is no friction and mass of the system, then we also need to know what is the position of that other end, so that, because the other end will also get some T force, tension force, and this will also get some T tension force. Okay, that's it. Now moving ahead. So there is one method of solving constants in case of massless string and inextensible string. So the basic thing is that the mass of the string is 0 and it is inextensible, means the total energy the string will have would be 0. So it means you cannot do, the energy of the string will always be 0, so you cannot do any work on the string. No network would be done on the string at any instant of time. So the summation of the work done on the string by all the bodies on the string means sum of all the work done on the string would be equal to 0. That is, the at each point where this string is connected with the body, there would be some tension acting, and the body and that point may have some dx displacement at any instant for a small interval of time, and the work done by each of these tension by the other bodies means, because we have action and reaction forces, when we apply some t1 force, there is some reaction t1 force, t force also, and that would tell us the work done by the other bodies, and that sum is equal to 0. For example, there is a case given here: three masses are given here connected by the rope, and this is connected like this, and this whole system is moving in this direction. So the work done by this mass m3 on this string would be, let's say this body makes some dx displacement, so we will say that this mass applies some t force in this direction, so we get minus t dx work by this when this displacement, when this string displaces dx in this direction, and this mass at this point, this mass is applied by this t force in this direction and t force in this direction. So these two forces would also be applied by the mass on these two, so the net force applied by this mass is 0, and that is work done by this is 0, and now this mass m1, this applies some again t force, and that will give us plus t dx, and that should be equal to 0, which is true. And there is another equation which is tv, and now this equation is useful in those cases when we have some angle. Let's say if I make it move on this slope, then in that case we will have this point moving in this direction, and I can tell the displacement along this slope by using this equation. Let's say it displaces by dy distance, then I can tell the work done by this. But I also need to know the direction of the tension. We have to take the tdy in that case. So let's say if there is a slope here along which this body is moving, so I will have to take the component of t. So if this is making some dy displacement in this direction, and this is, let's say, t tension in this direction, so I will have to take, let's say this angle is theta, so I will have to take t cos theta dot into dy. So that would be the work done by the string on this mass. So the negative of it I will have to take, that is minus t dy cos theta, and that's how I can tell the relation of the displacements. So in this last equation, when we differentiate it, we get this equation, but sorry, when we divide it by the time, we get, when we divide it by the dt time, we get this equation, but when we differentiate it with time, we get this equation, but that is only when this, because there is a cos theta also here, so we have to differentiate it also. But if that cos theta is also constant, means each angle is constant, then we can simply write this in this form. So that is the condition. And now in case of pulley, when there is a system like this of pulley, and in that case this whole system can be treated, let's say this is mass m1 m2, this is 0 mass pulley, then this whole system can be treated as this single body, and with some, let's say this pulley was accelerating with some ap acceleration, then this body is accelerating with some ap acceleration, and this effective mass of this body is 4 m1 m2 divided by m1 plus m2. That is the normal effective value calculate multiplied by the 4. Okay, so there is one more formula for a third released from the initial state, that is, let's say there is a frictionless surface, and this body has some mass density, linear mass density lambda, and total length L, gravity is in the downward direction, and this surface, the height of this point is, let's say, y2, and this is y1, and there is some t1 tension applied in this direction and t2 tension applied in this direction. First thing is that, okay, nothing. So there is some t1 tension applied here and t2 here, and in that case the equation of the acceleration of this body, let's say this point would be accelerated with some acceleration a in this direction, this would move in this direction, this moves in this direction, means they all move along the tangent and with some same acceleration a, and that equation of a is given by this. The a value of a can be given by this equation, where y1 t1 are here, y2 t2 are here, and we have to take the, let's say this is the direction along which we are taking the acceleration, so we have to subtract from this t1 and t1 minus t2, and then y2 minus y1, we have to take this height if we want to take the acceleration in this direction. So let's say if the acceleration value comes out to be negative, it means we had to take this value t2 minus t1 y1 minus y2 in that case to get this positive. So that's it. Now if let's say I don't apply any tension force at this end, I am only applying tension, means I'm only pulling at this end with some F force, then in that case this end would have zero tension force, means the state T2 will become zero if I don't apply any force here, means the free end of rope, free end means you are not applying any force at this point, and that is also the end point also. So in that case that tension would be equal to zero at this free end. Now for a double mass system, when one is pulled out with F2 force and another is pulled out with F1 force, F1 is M1 mass, K is the spring constant, or let's say there is some combination used and the effective spring constant is K effective, then in such case the maximum extension of this body, let's say this F1 and F2 are constant forces, then the maximum extension of this body would be equal to 2 times of F1 M2 plus F2 M1 divided by K into M1 M2, M1 plus M2. And there is one more thing, that there would be equilibrium, means there would be a state achieved when there is equilibrium here, and the fuck. Okay, so if I take only one force here, let's say this F2, and I remove this F, then there would be a point at which this mass would be at equilibrium, and that state is x naught is equal to x max by 2. That one means if one end is connected to a rigid steady body, then we get the, and for the rigid mass we can take the mass to be infinity. Okay, so x max, if its value is positive then it is expanding, then if it is negative then it is compressing. And the meaning of parallel and series combination of spring, parallel means they have the same expansion, means both springs when have the same extensions, then they are called in parallel combination. For example, this or this, these two will have same extensions, means if I move it by x, it will also move by x. But the thing is, it is possible that in one the force decreases, in other it increases, but in this case the force will always increase for both or decrease for both. In this case it is possible that it is increasing for one, decreasing for other in some cases. And series means the sum of the extensions is equal to some, okay, sorry, in series combination we have all the forces of the spring equal, means the force on this spring, that is let's say F, that is also the force in this spring, so in that case we call it series combination. Now to know how do I solve this question, this was solved just by taking an element here and taking its components, means in such cases we can take the, let's say this is the arbitrary body at any angle that is theta here slope, and let's say this element, I'm taking an element of this uniform rope, let's say dl, and in that case it would be having some dl into lambda sine theta g force along this direction, it is the mg sine theta in this direction, there would be some mg cos theta in this direction, that is d lambda cos theta z in this direction, and let's say this height, this is dy and this length is dx, this height is dy and this is dx and this is dl, so we get this dl sine theta is equal to actually dy, so this dl sine theta can be replaced with simply dy, so this value becomes this, and the total force acted along parallel to this tangent, if I take the summation of all of them, I will simply get a delta y into lambda g, so from that we get this expression, and t1 plus this, so let's say if I'm taking the expression in this direction, I will get t1 plus delta y lambda g, let's say this is y1, this is y2, minus t2, that would be equal to the total mass, that is lambda l into acceleration. So that's how I get this equation. And for this case we first write the equation of each of these bodies acceleration, so there will be some force constant here, let's say this extension at any instant is x, so kx is in this direction, kx in this direction, we get acceleration of both of them, and then we have to take the relative motion. So one more important thing here is this system was started from the rest, when the system started from the rest, then we can use this equation only, and in that case initially both bodies will have v1 equal to v2 is equal to 0, and if I take a relative motion, the maximum expansion means the body is not no longer stretching, means they are coming closer and they are also not going further. Sorry, let's say a body is expanding, or let's say expanding, so if it is expanding at any point, their relative velocity will become 0, so that after that they start compressing, means they will expand, and then at some point, let's say they are moving and expanding also, and at some point they expand max, and then they are start decreasing in size. So at the maximum expansion, the v1 and v2 velocities should be equal to each other, so means initially the velocity was 0, and when the x max occurs, the velocity should again be equal to 0, and that is similar to collision in case of compression, that two particles are here and they are colliding, the maximum compression occurs when they both have the same velocities. So we just have to write the equation of relative acceleration, relative velocities, and the relative velocity starts from 0 and goes to 0, and we just have to equate this. We have to just integrate this equation. Dx to 1 goes here, and this relative displacement between them is also the extension of the spring, and this delta v square by 2 value would be 0. Final and initial both would be 0, and this equation when integrated with x would be equal to 0, and solving this we get this equation. Okay, one more, any other thing. Okay, so pseudo forces. In case of pseudo forces, we have for let's say any frame S is there and I have to take the frame. I want to solve the question in the frame of S. Then in that case, let's say this frame is accelerating with some constant a acceleration. That is acceleration of the frame. So if I want to take the frame of S, so in the ground frame, let's say in an inertial frame, if I watch this frame from an inertial frame, first of all, inertial frame is always correct frame with no issues. But let's say this is an accelerating frame, that is non-inertial frame. So in that case, let's say it is acceleration, then if I have to solve from its frame, I have to sit down this frame that is accelerating. Then in that case, there would be some pseudo acceleration as I have to add this pseudo acceleration on each body. Means it does not add on the acceleration values. What it does means, let's say there is a body here, and okay, so this acceleration value will be added to each of the bodies, but in opposite direction. Means we have to add minus of this a delta s, that is called pseudo acceleration, a pseudo on each bodies. I have to add this value, and that pseudo acceleration when multiplied with the mass of the any body, that would tell me the pseudo force on that body. If I am seeing from this frame, pseudo forces all not real forces, means unreal forces. These only act in the accelerating frame, and real forces act in all frame. And if let's say this was a translating frame, only translating, so if there is a frame, let's say S with some x, y, let's say these are coordinates, and this frame is rotating with some omega. So let's say there is a point here S that is completely rotating, only rotating. If it is only rotating, then we have to take so any point from its frame that is at some r distance. For that point, we have to take some, since this point is would be accelerating in this direction with some omega square r from the ground frame. If this whole system is rotating, so with respect to this point, this body would have some, if this body is rotating out this point, then this body would have some centripetal acceleration omega square r. So I have to solve, if I want to solve from this rotating frame, this is at rest now, so it is also an inertia frame, but now what I say that if it starts rotating, so in that rotating frame this body want to be rotating, and in that case, in that rotating frame I will have to take omega square r minus omega square r vector, sorry, omega square r vector as a pseudo acceleration pseudo at any r distance. So it is a function of r also in the pseudo frame. So in the pseudo frame we have to take the frame of the point, this point on which we want to find the force. So if I want to find the pseudo acceleration at this point, I have to actually sit at this point. Okay, in this frame, and if let's say this frame is accelerating with some a acceleration also, and it is rotating with omega, then this body, this point will have some minus as pseudo acceleration plus some plus omega square r vector. This would be the pseudo acceleration of this point in that case, and multiplying this pseudo acceleration with the mass would give the pseudo force. Okay, sorry, son. And okay, one more thing, for solving any case, for example, for solving any question in which there is a, let's say, a block here, and it is placed on a wedge, and this surface is, let's say, frictionless, both surfaces are frictionless, this is mass m, that is capital mass m. So any question in which there is such a system which is released now, then in that case what would happen, if this body starts accelerating and this mass starts accelerating with some acceleration, if this mass m is accelerating with some acceleration, there would be some relative acceleration normal along this normal, means let's say this angle is theta, then there would be some a cos theta relative acceleration between, there would be some tendency of this mass m to accelerate in this, there would be some component of this mass accelerating in this direction, so that would reduce the normal force. Means if this body is accelerating in this direction, there would be some component of this mass in this direction, so it would look like the floor on which a person is sitting that is falling, and therefore the normal force will also decrease. So in that case the normal force will decrease, and if the normal force decreases, the acceleration of this mass due to this normal force will also decrease. So what I'm saying is that the normal force is causing this acceleration, and if this acceleration occurs, this normal force tends to be lower. Means there is a cause. Normal force is the cause here for this acceleration, and this is the cause, and this is the effect. So cause is causing some effect, and the effect is in return changing the cause. Means it is just like change of flux when producing an EMF. Means there is some changing flux, and that changing flux produces current, and the current then changes the flux again. So there is a state for solving such kind of problems in which there is a cause causing some effect, and effect is affecting the cause, effect is changing the cause. So in such case of complicated problems, we just have to assume that there is some a acceleration. Once we assume this a acceleration, we can solve this. We can find the equilibrium state for this acceleration and normal values, so that there is no change between them of them. And for example, to solve this question, or let's say I'm solving. Okay, let's first solve this question. This is mass m, this is capital M, this is angle theta, and let's say this angle would be 90 degree, and this would be, this is horizontal, this is theta, so this is 90 minus theta angle. So the normal force is acting in this way manner. Now normal force is a real force, it will act in all frame, and there is a gravitational force mg sin theta here, mg cos theta in this direction here, so both are real. Now what happens in the frame of wedge? Let's say this wedge is accelerating with the acceleration, I have to assume it. So if I sit on the frame of this wedge, there would be some pseudo force on this mass m, that is ma, in this direction, normal in this direction, and on the wedge there would be some normal force, and there would be some mg cos theta also. Sorry, only normal force would be there, because normal force is the sum of all the net acting forces. So mg cos theta was acting in this direction, and mg sin theta was acting in this direction. Now this angle is 90 minus theta, so this mg cos theta is acting downward, and because this body is not moving up, it means that the net downward force would be cancelled out by this and reaction normal force. On this mass there is some mg sin theta acting downward and m acting upward. Sorry, mg cos theta minus this component would be mg sin theta. So this normal force would be equal to this force, so that the net downward force equal to net upward force, so that this block remains in contact with this body. Initially it started with same velocities, means they were at rest. So we just need to make sure that their relative acceleration is also zero along this normal, so that they don't separate. And now this can slide along this with some mg sin theta force in this direction, plus some plus ma cos theta force component in this direction also. That would be giving it some acceleration in this direction, that is, let's say, a acceleration in this direction. So we get one equation, this, and another is this normal equation. We first make this normal equation for this body not separating with this mass m. Now this normal force would act on this mass capital M n to accelerate it. So the n sin theta component in this direction would be causing some acceleration of this mass, that is equal to this. So solving these two equations, I can get the value of normal force or a force. We can just eliminate one of these values and we get the value of a. So that's how we can solve, and after solving a, we can solve the value of a, and this a value is relative to this wedge. To solve the total velocity of this a, we have to take the vector a plus the vector a, that gives the a of m net. And this can be same thing happens in many other cases, many complicated cases. Now